So how to calculate this A? Remember back that A is the area through which the water pass. So imagine this is your wheel or your runner. So this is the flow of water. So this is the side view. And this is a view from the in front. So this is the water. Okay. So water flow pass through the wheel. So this is the area which is x1 multiply with x2. So we get the area. So this is the side view. So this is the area below here. So this is the area. When you in this picture, it's from the in front of the wheel. So we have x1 multiplied with x2. So number 5, theoretical estimation of electrical power output. So in practice, not all mechanical power available from the water flow can be usefully converted to electrical power output. There are losses occur in the system. So this is type of losses that always occur in the micro hydro system. Okay, this is from the channel. Okay, from channel we assume from the intake we have full power potential, and then the water flow through the channel. So from the channel losses 5%, and this is a 4 bay tank. So for water flow through the penstock, another 10% losses. And then from the turbine, another 20% losses. And convert into electricity with using generator, another 50% losses. If they have a transformer, another 4% losses. And then for the transmission line, another 10% losses. So P electrical equals to efficiency of the civil. Okay, efficiency of the civil, which is come from the channel. So this is the civil work. So 5% losses. So 0.95. Another losses from the fan stock, which is 10%. So 10% efficient fan stock will become 0.9. Efficiency of the turbine typically is 80%. So efficiency is often higher with larger and more modern turbines. So if 80%, so this one becomes 0.8. And then efficiency from generator. Typically, efficiency from generator is 85%. Then losses from transmission line, 10%, so 0.9. And then multiply with the full power potential. This is without any losses. So this is the full power potential multiply with all the losses. So we have 1, 2, 3, 4, 5. 5 losses. So transmission line, typically efficiency is 96%, mean 4% losses. So thus, the estimated overall efficiency become, when you calculate all, you will get 0.56 or 56% only. So in general, overall efficiency of the micro hydro system is between 0.5 to 0.7. Usually for full power potential, which is less than 10 kilowatt system, efficiency factor is about 0.5 to 0.6. But if the full power potential, which is the system more than 10 kilowatt, efficiency factor is 0.6 to 0.7. So the expected amount of electrical power output received is based on the following equation. P electrical equals to overall efficiency. So this is all the losses multiplied with rho QGH. This is the same thing that we learned before this. Density of water. This is the usable flow rate in cube meter per second. This is G, gravitational strength 9.81, and this is the head in meter. So example, a site has a gross head of 10 meter with flow rate of 0.3 cube meter per second. Determine the potential electrical power output. So solution. So we have this Q 0.3, and this is the H, and this is a water flow rate. So rho equals to 1000 kilogram per cube meter, multiply with 0.3 Q, multiply with gravitational strength 9.8, multiply with head 10 meter. So for full power potential without any losses, we get 29.4 kilowatt. In case after we calculate all the overall efficiency, okay, including all the losses, we only get 0.65. So the output P electrical equals to, this is overall efficiency from all the losses, 0.65 for example, multiply with full power potential. So lastly, we get P electrical including the losses, we get 19.11 kilowatt. Number 6, determine the water flow rate Q. One of the important parameters to estimate the power output from the microhydro system is the water flow rate. So the flow rate Q is the quantity of water flowing past a point at a given time in cube meter per second. So there are many methods to measure water flow rate. Some of those methods are as follows. So the easiest one is using bucket method. Number 2, float method. 3, weir method. Number 4, salt dilution method. And number 5, flow meter. Okay, we start with first method to measure the water flow rate by using bucket method. Bucket method are very easy method to estimate discharge is to simply measure the time it takes to fill up a container of a known volume. So this method only works for systems with fairly low flow volume. Its main limitation is that the discharge must fall from a pipe or ditch in such a way that the bucket can be placed underneath it to capture all the discharge. Any size bucket can be used as long as it does not fill up too fast to get an accurate measurement. So every time you fill up the water, you need to measure the time. So in this picture, this is an example from the water flow. So 100% water from the pipe go through the bucket. So the method is fill a container of known volume in cube meter with the water existing the pipe. So make sure you take the timing in second, how long it take to fill up, and then conduct this measurement several times and calculate the average. Calculate how many cube meter would exit the pipe in 1 minute. You now have your flow in cube meter per second. Example, you have a container with known volume which is 20 liter. So average time taken to fill up the container. So you already calculate the average, which is 15 seconds per container. So container volume 20 liter. 20 liter we convert to cube meter, so 20 divided with 1000. So average time taken to fill up the container, which is 15 seconds. So therefore the water flow rate 20 over 1000 divided with 15 seconds. So the water flow rate is 0.00133 cube meter per second. So another method to measure the water flow rate is by using float method. So the float method is an adequate means of estimating flow, especially in circumstances where a flow meter is not available, or when the water in the stream is not wettable. This method is simple and inexpensive to perform. This method requires the measurement and calculation of the cross-sectional area of the channel as well as the time it takes an object to float and designated distance. So this is example of the float method. It's actually you need to make it far, but this is only the illustration. So example here you have 15 meter. You need to take a timing using stopwatch. So this is the starting point and this is the ending point. So this is the least accurate method of those presented in this note, but does provide a reasonable estimate. The simplest way to measure flow is via a 4-step process. So number 1, measure the speed of the surface water in meter per second flow using float object. So number 2, determine the cross-sectional area of the water source in square meter. Calculate the surface flow rate. So surface flow rate equals to surface velocity meter per second multiplied with cross-sectional area of the river. So how to get this surface velocity? To get this surface velocity, you must make a timing here. So this example 15 meter, and let's say the object float starting from here to here, it will take about 10 seconds. So 10 meter here divide with 10 seconds, and then multiply with the cross-sectional area of the river. So you estimate or you measure the cross-sectional area of the river. So actual flow rate for this method, surface flow rate that you calculate in number 3 multiply with correction factor. So this is type of losses factor for each type of the river. So example here, correction factor. Let's say the stream is from the concrete channel, rectangular and smooth. For example here, man-made stream. So the correction factor is 0.85. If the stream comes from the large, slow, clear stream, so 0.75. If small, slow and clear stream, the correction factor is 0.65. If is it shallow, which is less than 0.5 meter or 1.5 feet, and turbulent stream, so the correction factor is 0.45. And very shallow and rocky stream, so the correction factor is 0.25. So this is the example of the people measuring the water flow rate by using float method. So this person measure the shallow, the shallowness of the stream, and also they try to calculate the area of the river. So this is the starting point and this is the ending point. So let's say example for the float method. So given average time taken for a float object to travel in 15 meter is about 150 seconds. So this is already average. Okay. So let's say you take a few time, you float the object for distance 50 meter. Let's say 5 times, you average the time with 5, so you get 150 seconds. So let's say the stream is concrete, rectangular and smooth. So your correction factor will be 0.85. The width of the channel 5 meter, you measure 5 meter, and the depth of the channel 3 meter. Thus average surface flow rate, so 15 meter divided with 150 seconds. So you get 0.1 meter per second. So this is average water flow rate. And then cross-sectional area of the channel. So this is the area A, 5 multiplied with 3. You get 15 square meter. So the actual flow rate, so average flow rate multiplied with cross-sectional area of the channel multiplied with, this is the losses or correction factor, 0.85. So you get the actual flow rate Q actual equals to 1.275 cubic meter per second. So another method to measure the water flow rate is wear method. So this is the wear method. So this is the wear using timber. So this is the most accurate method of measuring the flow in medium-sized stream. So a flow measurement weir has a rectangular notch in it through which all the water in the stream flow. It is useful typically for flow in the region of 0.05 to 1 cubic meter per second. So very low flow rate. So they have this rectangular notch. So this is the rectangular notch of the weir. So the weir is built like a dam across the stream, which causes all the water to flow over a rectangular notch of known dimension. See figure below. Okay, so you know the dimension of the notch. For example, here this is the width of the notch. Okay. The weir is best constructed with timber and made watertight with sandbag, salt or clay. So the water flow rate can be determined from a single reading of the difference in height between the upstream water level and the bottom of the notch. So the one is from the height of the upper stream water level. So this one D until the opening of the notch. Okay, so this is the level of the water upper stream until the opening of the notch at the edge of the notch. For reliable result, the crest of the weir must be kept sharp and sediment must be prevented from accumulating behind the weir. So this is the crest. The crest here must be sharp. Okay, so all the sediment left out on this side. So the water flow rate using rectangular notch weir is Q equals to 2 over 3 CD. CD is the coefficient of discharge. insert 2 multiply with g. So g is the acceleration due to gravitational strength, which is 9.81 meter per square second, multiply with length, okay, length of the notch, but in this figure they put w. So this w actually equals to L, which is the length of the notch minus 0.2 h. H is the depth of the wear crest below upstream water level. So this H actually is the D, okay, from the upstream into the crest of the notch. Okay, multiply with H. This is 1.5. Please make correction here. This is H 1.5. So this equation is quite longer, but if CD is taken, which is typically 0.6, which is coefficient for discharge, usually 0.6, then we can simplify the equation into Q equals to 1.8, the length of the notch minus 0.2 H multiplied with H to the power 1.5. Okay. So this is the length and this is the H, okay, from the upper string to the crest of the notch. Okay, in this figure, H is actually D. So another method to measure the flow rate is by using salt. We call salt dilution method. So theory, the salt dilution method is a way to determine stream discharge or flow rate in cubic meter per second in small mountain streams that are often very turbulent. It works well in streams in which the flow rate is not too high, which is less than 10 cubic meter per second. The idea is to inject into the stream a highly concentrated salt solution. The salt solution will slowly mix with the stream water as it flows downstream. The concentration can be picked up with an electroconductivity meter. So by relating the salt concentration to the measured electroconductivity values, we can find the flow rate of a turbulent stream by finding the area of the salt time curve. So how to do this? So the injection point upstream and measuring point downstream have to be at least 15 times of the width of the stream apart. Procedure: at the injection point, start mixing the injection solution. To do this, you fill up 2 buckets with exactly 10 liters of stream water for each bucket. And then you add 3 kg of salt to each bucket and stir well about 5 minutes. Then you go to the stream and you record the background, EC, and then water temperature at the injection point. And then set up the conductivity probe at the measuring point. So this is measuring point, not the upstream or injection point. Again, you record background EC and the stream water temperature at the measuring point. So this is the measuring point we call downstream point. Okay, start now recording the stream water EC every 5 seconds. And then inject your prepared salt solution all at once into the middle of the stream. record the passage of the salt wave, continuing until EC return to background. So this is the result. Putting the measured EC, electroconductivity versus time in a graph will give a nice pulse graph when measured correctly. So without injection of the salt dilution, so this is the value of the EC base. Okay, the EC reading at the measuring point without salt dilution. Okay, after you put the salt into the stream, so the EC meter will start to read the conductivity until it go back to the base or go back to the breakdown. When the salt dilution is already passes through the measuring point. So the EC can be converted by sodium chloride, this is salt, equals to, this is the EC measured, and here is the EC base. So to get this area, of course, you must eliminate this base to get the accurate EC. So EC measured minus EC base. So you will get this area. Okay. Multiply with 0.58. 0.58 is a conversion factor obtained through the experiment. So this is factor for the salt dilution. Okay, this result in a new graph that is the sodium chloride concentration versus time. It should also show a nice pulse graph that should start from 0. So this is after you minus EC measured minus EC base. What we know is that the total pulse of salt concentration was caused by our added salt. So this is the added salts to the stream. This is the EC background of the stream. And here is how we get the concentration factor 0.58, that one for the salt concentration. So total area under the curve of sodium chloride is, now you calculate the area. So this is the area, the grey color A. So total area equals to, from start time to the end time, EC measured minus EC base multiplied with sampling rate in seconds. So the sampling rate of the reading, for example, every 5 seconds. Okay, so sampling rate is 5 seconds. So therefore the flow rate is Q equals to mass of the salt, for example 3 kg, convert in milligram, multiply with 1 over total area from this equation. Okay, so this is the area under the graph. Next one, measuring the flow rate of the water using flow meter. Okay, using this method, stream should be straight enough to have uniform flow. So the procedure are as follows. Tighten a measuring tape across the stream at right angle of the flow. It should be snug and not snag in the middle. Measure the total stream width and record this value. Okay, this measurement. Divide the total stream width into equal segments. If the stream is less than 3 meter wide, use 0.15 meter interval. So let's say the width of the stream is 3 meter. So you divide with 20. You divide into the equal segment. You divide with 20 segment. For 3 meter, you get 0.15 meter interval. For stream greater than 10 meter, so use 0.3 meter or greater interval. So please take note, the standard method is to divide the width by 20. So 1.5 again we get when we divide 3 meter with 20. So step out to the first measuring point and position the rod. And then you stand downstream from the measuring tape with the rod next to the tape. The rod should be held vertically, the meter should face upstream, and you should be standing off to the side or behind the meter. Record the distance to the bank. So measure total stream depth and record this depth. So multiply the total depth by 0.6 and set the propeller at this depth. Okay. Note 0.6 times the total depth is considered the point of average discharge in a spot that is less than 0.6 meter deep. If the depth is greater than 0.6 meter, two different velocity measurements are required. One at 0.2 times the depth of one at 0.8 times the depth. Read and record the velocity at this depth. So the propeller you need to put two different height. Okay, which is 0.2 and you measure 0.2 and 0.8 times the depth. And then move to the next measuring point and then repeat the process. Note the standard method is to obtain 3 velocity measurements at each point and average them. So make sure to record the distance to the bank, the total stream depth and velocity of the 0.6 depth for each point across the stream. So finally, the flow rate is a total of flow rate of each cell. So this is velocity at location number 1 and the area of location number 1 plus velocity at area number 2 multiply with area number 2 plus velocity of flow rate at position number 3 and area number 3. Okay, number 7, determination of effective head H. The head is the vertical height in meters m from the level where the water enters the intake pipe, which is penstock, to the level where the water leaves the turbine housing. So method 1 is by using surveyor transit or level and a pole. So this yellow color is a surveyor transit or level. Okay. So usually we use a liquid here. This is a liquid. Okay. To know the correct levels from this pole to pole. So you have one pole here, another pole here. This is the surveyor levels or surveyor transit. And then you get the height and the distance here. And then you put another pole here and here. And then you measure the level and the height. And another pole here to the pipeline intake. Another height and the distance. So hydrostatic head, you total up all the height or head, H1 plus H2 plus H3. Example here, head number 1 plus head number 2 plus head number 3. So about the penstock length, to get the penstock length, so you total up square root D1 plus H1, D1 squared plus H1 squared. Okay, and then plus D12 plus H12 and so on. Okay, to get the pipeline, the penstock length. Method 2 is by using water filled tube and pressure gauge. So using a pressure gauge for each point. Okay, example here, at point number 3, you measure from point number 2 to point number 3, you put the pressure gauge. So this is the intake of the pipeline and this is the turbine inlet. Okay. Note, use lowest gauge range and the highest elevation change you can get to minimize the pressure error. So hydrostatic head or pressure, so from all total up from the measure from pressure point 3 and then pressure point 2 and pressure point 3, so you total up, you get the head. So penstock length estimation, same concept with the first one. So distance 1, head number 1, distance 2, head number 2, distance 3, head number 3. And then you convert the reading, pressure to head 1 psi equals to 0.704 or meter for water. So another method to know the head. Number 3 is by using tidal light with ridge finder. So this one is the easiest one using the technologies. We measure the slope angle using tidal light and measure distance using tape or range finder. Okay, so this is the tidal light. Then the vertical height of head can be determined. Okay, sizing technique. Sizing technique of the microhydro system can be divided into two, which is sizing based on the peak power demand and the sizing based on the base load. Okay, let's see sizing method number 1. Sizing hydro system to meet peak power demand. You tabulate the load profile and then you determine the peak power demand. Size the generator to meet the peak power demand. Divert excess power at off-peak time using an ELC, electronic load controller, into ballast load or dummy load. Example, you are planning to install a micro hydro power system that could supply AC peak power demand of 2.7 kW with power factor 0.8. You plan to use 24V DC alternator in your system. The effective head is 5 meter. What is the size of alternator current required? What is the minimum water flow rate to sustain the operation of the micro hydro? So you need to calculate the I for the alternators for this 30V DC alternator, and also Q minimum when the micro hydro start to operate or start to give the output. Since the load is an AC type, you need to use inverter in your system, assuming inverter efficiency is 85%. So this is because we have this DC alternator. So if the load is AC, we need an inverter. So here is the solution. Therefore, the minimum output required by from 34V alternator is So IDC, this is power divided with voltage. So 2700, don't forget you have power factor, so you divide with 0.8, multiply with 1/24, this is 24 volt. So power divide with power factor multiply with voltage. So you get 140.6 ampere. So thus you can use 24 volt alternator, but choose the current which is higher from this IDC minimum. For example here 150 ampere type of alternator which is commercially available. Assuming that overall efficiency is 50%, then the minimum water flow rate required could be derived from P electrical equals to overall efficiency multiplied with raw QGH. So this is overall efficiency that you learned before this, okay, including all the type of losses. So therefore Q become the subject, so Q minimum equals to P electrical divided with raw GH multiplied with overall efficiency. So the Q minimum, the minimum flow rate that could required for this system is 0.0809 cube meter per second. So most of the time the load may not at maximum demand, so thus ELC, electronic load controller, should be used to divert surplus power to a dummy load. Another sizing method is sizing based on the base load. So you need to know the value of base load and then you calculate the, again same thing, you calculate the P electrical from the base load. Okay, if you know the size of the alternator, okay, and then you calculate P electrical, but that one for only for the base load. So size the of the generator to meet or slightly exceed the base load, and to meet the peak power demand, you need to use the battery storage and the inverter if required. So this technique is useful when the power output generated cannot meet the peak power demand. That means the generator or the system, the stream cannot meet the peak power demand. So the size of battery required can be designed such that it just adequate to supply power during peak power demand and it usually not large. So again we use ELC is also used to dump surplus power to dummy load, thus prevent from overspinning of turbine during low load, especially when the battery is fully charged. Okay, principle and assessment of the microhydro system. So we need to know the capacity factor. Capacity factor is an indicator of how hard a turbine is working in a year. So capacity factor equals to energy generated per annum. So this is energy generated from the system in kilowatt hour. And then rated output power. Rated output power is the rated value from the alternator. And then you multiply with 365 days and multiply with 24 hours. So from this one you get the energy, rated energy from the generator or alternator. So it is quite common that your CF for the microhydro system should be greater than 50%. It's quite common in practice, the CF for microhydro is greater than 50%. So indicate that the microhydro system design is good. So load factor, the load factor LF is defined as LF equals to average load divided with maximum load multiply with 100 into percentage. So typical load factor for microhydro is in the range of 35% to 40%. So next one, hydroelectric system. Sometimes they use synchronous generator. In some countries, example Vietnam, in expensive small size synchronous generator up to 20 kilowatt, both three-phase and single-phase are available in the market. These generators are suitable for village hydro. And sometimes they use induction generator. So this is example of the output of the induction generator. So this is the output from 2 to 20 kilowatt with a different rated current, but the output is single phase and a different weight. So they have two common connection, CCC connection for three phase, and this is for the single phase C22C connection. So here is the example model for output kilowatt induction motor 1.1 kilowatt, 1.5 until 3 kilowatt. And you can see here with a less number of pole, it produces a rotation speed which is much higher. So hybrid hydro generator system. So micro hydro can be combined with genset or other renewable energy system to form a hybrid system. So example here we have generator combined with micro hydro system and the battery. So micro hydro, so the output is AC, and then we need a rectifier to convert to DC to charge the battery. And for generator is also AC. We need to convert AC to DC by using charge controller or battery charger. And then if we have AC load from the battery, convert into AC by using inverter. So maintenance, common problem with micro hydro power system. First, loose battery connection or the T terminal. Number 2, intake point covers in leaf or debris, resulting in turbine not receiving enough water. So intake line has been damaged. Inlet valve or jet in turbine are blocked, or winding in turbine have burned out. So rectifier in DC unit has failed, so no DC output. Regulator unit has failed and does not allow power to reach load. Bearing failure, so noisy operation, and inverter failure. So that's all for this chapter. So thank you.